Hi, I'm Walter Grayman, representing the Environmental and Water Resources Institute, that's EWRI's WDSA History Project. The purpose of this project is to document the history of water distribution system analysis. An important part of this project is a series of interviews with engineers, modelers, researchers, and practitioners who have made significant contributions to the field of water distribution system analysis. Our interview today is with Dr. Uri Shamir. Uri has been in the forefront of water distribution system analysis since the 1960s and continues to make significant contributions. His work in academia, Technion, MIT, and others, consulting, government, and professional organizations have all contributed to his well-deserved reputation as one of the true icons in our field. This interview is being conducted on May 19, 2015 in Austin, Texas. Uri, you've been working in the field of water distribution system analysis for over a half century. It's a little scary, but can you remember how you first got involved in this area?
I was at MIT and I was required to demonstrate capability in systems analysis. And so I undertook a summer project to optimize a distribution system. I selected the problem and demonstrated that I could use optimization to determine the optimal diameters for a simple gravity-fed distribution system. I handed that in, it got a high grade, and I was hooked on distribution systems at that point in time. Immediately subsequent to that, Chuck Howard, my friend, left MIT when he completed his studies, went to work for a local consulting firm, and got me as a consultant to work on the Boston water study. And based on the fact that I had already dealt with distribution systems. That was basically the trigger. From there on, all of the motivation, or most of the motivation in my work, resulted from actual practical problems that we needed to address. And we looked around, Chuck and I looked around for the techniques that were of the time, and found out that they were lacking in terms of what they provided to engineers in dealing with real problems. So from there on, it was basically a matter of looking at real world problems in the context of a particular project for a particular client, and creating the tools that are required in order to address that in the most meaningful and efficient way.
You mentioned Chuck Howard, and I must say there's a lot, I know you've had a lot of connections, and you'll frequently see them referred to as Shamir and Howard, or Howard and Shamir. Can you talk a little bit more about the relationship and kind of the creative milieu that it worked in?
Well, I'll give you the anecdote. It starts in the lab at MIT. I came back from class one day, and there was an opening in the floor through which Chuck was pouring concrete for his experimental setup in the basement, and there were about 10 research assistants standing with their hands in their pockets looking at the way he was humping concrete in a wheelbarrow. And I went to my desk, dropped my stuff, and came back, picked up another one, and we worked together. And that's how we cemented our friendship. So, but Chuck has been a consultant all his life. After leaving MIT, he started working for a consulting firm in Boston, and then moved on and had his own, first with partners and then by himself. And over our entire joint career, I have been working with him on consulting jobs, and practically all of our joint publications are the consequence, the result of advancing the state of the technology of dealing with problems, not only in distribution systems, but in this particular case, we'll concentrate on distribution systems. So much of the work that we did together was generated to meet the needs of a particular project in the most effective way. And we've remained lifelong friends. We spent a lot of time together. I used to go to Canada practically every summer and help in the consulting firm, Charles Howard and Associates. And we did a lot of stuff together that we'll talk about probably in a few minutes.
I think most people know you as a professor and other positions at Technion in Israel, but you've also done a tremendous amount of consulting, government work, research, and there seems to be, I mean, you've emphasized practical applications, but doing it in a scientific manner. Can you talk a little bit about that in terms of your career?
Well, the proof of things being innovative is in the fact that the results appeared in high-quality journals, like Water Resources Research, the Journal of the Water Resources Planning and Management Division of ASE, and others. In other words, they qualified as scientific contributions. And it was always because we went beyond the existing tools. What existed at the time and what was taught in classes in universities did not satisfy us and challenged our curiosity and our capabilities. And so we evolved new mathematical models and ways of solving them. And the result has been a set of technologies that went out into practice. And they always resulted from a need in the field.
But I think you've been more successful than many, this is my impression, many academicians who do good scientific work, publish it in WRR or other journals, but it doesn't seem to then have much impact in the field. How have you made it such that your work has had the impacts in the practical?
Well, as long as we were doing studies, I was doing studies that resulted in a specific plan in various parts of the world, that can be in Holland, in North America. It was the specific solution that was generated for that project. But as far as the scientific part is concerned, as I say, it resulted from the fact that we needed to address a specific project or specific problem that was on the ground, and I can give a few examples of that. I'll give you an example in distribution system solutions, which resulted in our 1968 paper in the hydraulics division at ASCE. The conventional wisdom at the time were models that used either Hardy-Cross or Martin and Peters, which was a Newton-Raphson based. But in these formulations, it was always given a network and given the demands, solve for the flows and the heads. And when you go out into the field, you have little idea about the consumptions. The pipes in the ground are what they were 20, 30, 40 years ago, so you don't have enough about that. But it's easy to measure pressures, easier than measuring other things. So can you turn the problem around? And it's the following. You are solving a set of simultaneous, nonlinear algebraic equations, and let's say that you're solving the node type of equations rather than the loop type. So you have n nodes, you can solve for n unknowns. And these n unknowns, we claimed at the time, and it appears in the 68 paper, can be a mix of three types. They can be heads, consumptions, and link resistances. They have to be spread throughout the network so the resulting set of equations is solvable. You can't put them all in one corner and so on. But that's what we did. That paper shows that you can formulate the equations and take out the unknowns or put in the knowns that are best known in the field and solve for those which are least known. That can serve for calibration. It can solve for optimizing operation. It can do a variety of other things. For example, sensitivity analysis comes out automatically from the results because you have the final set of equations are solved with a Jacobian, and that Jacobian serves you in order to find the sensitivity of all the unknowns with respect to changes in knowns. So here it was a situation where we felt that not doing it this way required a much larger set of trial and error runs. This way you could hone in much more quickly into those things that were of relevance to you. So we turned the problem around. We reformulated it. We looked at it as a set of simultaneous equations. We know that we can solve those if they are solvable, rather than going the automatic way and using the conventional formulation. And the same thing happened several other times in our history. I'll give you one more example, and that's not changing things around. I was in Calgary at one point in time, working on the distribution system that was receiving water now from a new source called Bear Spa, and the engineers were running a 200-node network in order to figure out how to best connect the new source of supply. I came in, I took one look, and I said, why do we need this very detailed model? Because we're not really interested in the pressure and the flow in each small pipe. We want to see the overall map of flows and pressures. And I reduced a 200-node network into a 19-node network, which is a surrogate of the real one, calibrated it so that it operated like the full model, and then instead of running a run, each run was then $100 for the 200-node network. The cost of a run that was only 19 nodes, which was 1/10 of that, is 1/100th of the cost of a run. So instead of $100 a run, it was $1 a run. And for $1, you can run many runs and try a lot of other things. And then it was translated back into the full thing. So by necessity, or by thinking about the problem, we solve it in a different way. One more example. In the same place, while I was doing this in Calgary, over tea in the afternoon, the city engineer, Jim Bauk, said to me, listen, we have 1,000 pipe breaks a year, and we spend about $1,500 per break. That's $1.5 million a year for fixing pipes. And we don't know whether to replace a pipe or to fix it. And in an afternoon, really on the back of an envelope, I developed an economic 101 type model that said what is the optimal time for replacement if the breaks increase over time and the present value of replacing goes down the further you defer. And we published that with Chuck in, I think it was 1980. The net result is that there is a whole industry in this country, in the United States, that deals with pipe breaks, and I still see at this conference we are today, a refinement on a refinement or a refinement of the model that was a very simple model and helped the city of Calgary to address this problem of when do you replace, when do you fix.
You referred to that case where you were able to reduce the system into a much simpler one. Today we have, with such large or powerful computers and models, it's not unusual now to find models containing 100,000, 200,000 pipes, and we do that. Are we somewhat substituting brute force for the more creative processes in the past?
The question is, what are you trying to address in the problem? If you want to see the great detail of what's happening, you just, today, with today's capacity, you do that. If the question is what we had at the time, namely how to connect effectively a new source into the city, what is of interest is not the existing system at all, but will the farthest point receive enough water? Will the hospital at the high point on a hill be served? Will the system operate as a system? And so what you do is you look at the problem that you're facing and you ask yourself, what is the appropriate level of detail you require? And that's when I invented the term gray box. White box is what you're talking about. Everything is in there, even though not everything is in there, because below 6 inches you don't stick them in. You usually use some minimum diameter, and that's already a skeletonization of some sort. But a black box would be an input-output like we have in hydrology. And a gray box has the level of detail that is appropriate for addressing the problem at hand. So the same network may be solved different times with different levels of detail, depending on what it is that you're after. Now, the size of the network, even if you can solve with tens of thousands of say, pipes, whatever it is, The larger the problem that you're trying to solve, the more prone it is to mistakes, the longer it takes you to solve, the fewer runs you're making, the more you're paying attention to this great detail, and you're not necessarily extracting from that the insight, which is the most important output, rather than just the numbers. And looking at all these numbers on a very large network may not be conducive to looking into the solution and finding out the overall operation of the system. Well, this has also resulted in a lifelong way in which I address things, and all my students have learned from me that when they start developing a model and begin to have some output, some results, I warn them in advance that I'm going to pull the plug on the computer. In other words, they're not going to be able to make another run, and they will have to answer questions, what if? What would happen if I multiplied something by 2 or reduced something or changed something in? Can they gain an understanding, a comprehension of the system and its performance before they make yet another run and rush to make one more run? So it's insight that I'm after. Then I also need the numbers and the results and the details and the pipe diameters and the pump characteristics and so on and so forth. But no less than that, and even more, I am seeking an insight to the way in which a system operates. And it can, then I go to hydrology and to water resources management, and so it's exactly the same.
You know, starting off, you mentioned your 1964 summer project where you did an optimization, and I think you had said with 11 pipe system. You've been very active in the optimization area for a long time. Can you talk about that a little bit and about concerns or issues in doing optimization?
Well, while I was studying, I took courses in electrical engineering, in the Sloan School, in mathematics, and got myself into systems analysis and studied the existing techniques at the time, dynamic programming from Ron Howard, linear programming from others, and so on and so forth, and immediately hooked the two parts, namely the physical world, which then has to include the economics and the environment and the institutional and so on, into a package of management. Again, because of a need in 1970-something, I developed the first substantial optimization method. I came back from a sabbatical at IBM's Watson Research Center, where I worked on optimization of distribution systems, and that was published as a report and as a paper in 1974. One of my PhDs immediately after that was working in a consulting firm, and they were dealing with a water distribution system in an African city, which is located on a relatively steep slope. And we could not make the network solution work. The reservoirs wouldn't fill as they should, they wouldn't empty as they should, the pressures were all over the landscape. And we fiddled around with the network using what I had already developed earlier, in other words, being able to release some of the unknowns, but still it didn't work. The net result of that was an optimization methodology that determined the parameters of the system, which we called LPG for linear programming gradient, was published then in Water Resources Research in about 1977, I believe it is. Together with a PhD student of mine, Alperovich. And it essentially decomposed the problem into two. If you set the flows in the entire network, you know what they are, they satisfy all the node equations and so on and so forth, you can optimize for the properties of all the network elements, pipes, pumps, reservoirs, and so on and so forth. So what you do is you first distribute the flows in the network, you solve, and the solution gives you the derivatives basically for how to change the flows in the network to improve the value of the objective function. And since the changes in the flow distribution have to continue to satisfy node equations and so on, We did an iterative process called LPG. G is for gradient. And by a sequence of flow, optimize, we improved the solution or the gut. And there is no guarantee for overall optimality, but it can definitely do better, for example, than what the engineer does. The engineer would give me the flow distribution that resulted from their design, and I said, on this I can improve by taking this and finding the derivatives of the cost function with respect to the properties of all the variables, and improve on that and get a better cost, starting from, for example, from an engineering design. We did that also for things that were not designed originally. We did from the very beginning. So that was optimization. And then a sequence of graduate students did that. Avi Osfeld is one of them, where we tied in optimization, added reliability to that. And again, it was an optimization process, in this particular case, first of the operation and then of the design of a distribution system, incorporating a variety of objective functions. Some of them had to do with the cost, others have to do with satisfying constraints and things like that.
Uri, can you tell us a little bit about the work that you've done in the area of reliability as related to water distribution systems?
It again starts with a practical problem. In the city of Calgary, we were looking at the issue of pipe breaks. I was asked whether or not we can help the city to decide when to replace a piece of pipe and when to fix it. And in so doing, we developed a very simple economic model on determining the optimal time. We realized as a result of that this rolled itself into a situation of reliability in water supply systems. And we wrote a completely theoretical paper, Chuck and I, that balanced the various considerations in reliability of water supply. It had no real data in it, except something that I had done in '72 back home in Israel, where we were trying to determine the reliability of a regional water supply system with a number of wells. And so we wrote a completely theoretical paper that really developed the shape and form of the various functions that go into the consideration of reliability. If you have a system that has storage and pumping capacity and demand and so on, we developed a set of curves. As a result of that, we went into two cities, into Ottawa Carleton in Canada and in Seattle. And we did a reliability analysis that added the economics into this. It looked into the losses associated with non-reliability, and we based that on demand functions, on the willingness to pay, which is a curve that goes, from due to the cost, shows you what the flexibility or essentially the elasticity is. And we used that elasticity and we developed a procedure for analyzing the reliability of the existing supply systems. We found out that the existing systems were usually highly reliable. That results from, I guess, the conservative attitude that water managers and operators have. And that rolled then back into the academia. And I had Avi Osfeld deal with reliability. That's part of his thesis. We then did a PhD thesis, and then we developed a whole set of models relating to that. And it went into the field, basically, and triggered an attitude to reliability that came basically from the water supply side, connected to the demand side, the willingness to pay or the losses associated. And it's become a standard thing to analyze. So again, it's a matter, or it's a case of combining an actual practical problem, being asked what is the reliability of the system, does it require updating or improving? And the methodology that was developed is essentially a cornerstone in the way in which we do reliability analysis.
Thanks. Through all your activities around the globe, you are truly a true citizen of the world. But you are a native Israeli, and you spend a majority of your time there. Israel certainly had and still has its share of water issues, and traditionally has dealt with them in a very creative manner. Can you talk about the contributions coming out of Israel and maybe shortcomings in the water resources area, and especially in the water distribution system field?
Well, Israel has had to face water shortage much earlier than many parts of the world. And as a result of that, we developed a set of approaches, methodologies, tools in order to analyze and determine both the operation and the capacity expansion of our system. But if you look back at the history, this started very early in the game, in the last century, basically. And so in many areas of water resources management, in particular water, groundwater systems, less so in surface water because we have very little of that, we have one lake. The result has been that we have been forced essentially or motivated to develop the approaches, methods, tools in order to do that. The world has caught up with that, and over time we have failed in many things. We did not manage to convince the political entities in Israel to do things early enough. As a result of that, we went through long periods of time where the water resources were being depleted and polluted over time until it became impossible. And that's when the advent of desalination kicked in the year 2000, 2001. And now we're in a very different situation. We have now 5 operating desalination plants that supplement the natural. They are not going to replace it. Natural waters continue to be basically a strategic asset. Added to that are the relations with our neighbors. We have a 1994 treaty with the Kingdom of Jordan, the Hashemite Kingdom of Jordan, on joint management of our water resources in the area. I am still part of the negotiating team with our neighbors. And when we crafted the 1994 treaty, it brought to bear basically our capabilities in water resources management. In 95, we signed the Oslo II interim agreement with the Palestinians. And again, the knowledge that exists in our professional cadre of people in Israel serves quite well both the Palestinians and ourselves in terms of moving ahead and addressing the problems with time. I am concerned primarily about the issue of whether or not the Israeli water sector has a sufficient number of younger people entering the profession. Maybe it's because the national authorities are not paying sufficient attention to that. We're still strong, but not strong enough, and definitely not improving our capabilities with time because the national authorities are really not paying sufficient attention, I think, to the need in a complicated world. You might be thinking that this is the result of Israel having solved all the problems. You know, we made the desert bloom, we have a national integrated water system, we know how to manage groundwater, and so on and so forth. But the world is becoming more and more complex with quantity and quality, and I'm concerned as to whether or not we continue to have the same capability to address future problems. So we're working on that. I think we're still in good shape, but I have a concern about the future.
I'm surprised a little about with your some note of pessimism, because we see it externally. We see a lot of Israeli companies developing technology that's being exported to us in the water field, in the monitoring field, in the operating field. So externally, it appears that they are very strong.
Well, you did touch upon the industry, and there again, the entrepreneurship that exists in Israel in all fields, in biotech or in nanotech, is also in the water field. And indeed, Israeli companies that have developed monitoring and other processes fare very well around the world. But the question is, are we managing our own water resources in an adequate manner? We still do. We have a very good system. But I am looking further ahead and asking myself whether or not we remain as strong as we need to be in order to address our problems and be able to be good partners with our neighbors, with the countries around us with whom we may share part of the water resources and so on. We're still, I would say, superior to anybody around in the area, but I would rather see them come up with their capabilities and Israel remaining strong in the local capabilities. Industry is faring very well all over the world, in the developed and developing world.
You know, this has been a relatively short interview, and it's hard to condense a half century of work in this short period. Anything else you'd like to share with us, and maybe your views on the directions for the future?
Oh, I have so much to say that I don't know whether we can condense it into. What I would say is that with the advent of methodologies and approaches, I have a concern about the amount of attention that we as engineers and our students pay to the understanding and insight of the problems that we solve. In other words, the advent of modeling that can crank out a lot sometimes cause people to be relatively lazy in terms of the time that they spend. We just heard the talk by Dave Ford about his experience, in which he quoted Albert Einstein, who said, if you're faced with 1 hour to solve a problem, you should spend 55 minutes thinking about it and 5 minutes trying to solve it. And all my students over the years have been taught essentially to spend more time on understanding the problem and understanding the solution that you're generating, rather than just cranking out results by the ton. So some of the techniques that are being used today, as neat and as elegant as they might be, I have a concern about them, because they do not require you to invest the same amount of thought into what it is that you're doing and what the results mean. And so, in a sense, it's a blessing that we have these capabilities, not only the computer power, but also the new techniques of various kinds. But it's also a curse if you don't impose upon yourself a discipline which says you're really addressing problems that are complex, and that you need to think about the problem itself, condense within it the essence, address that in the simplest possible way that you can before you begin to crank out a lot of numbers, and think about solutions which may be highly simplified and still give you a sufficient insight to begin to move into more detailed and more advanced techniques for addressing that. That is a point of concern that I've had all the years, and I can tell you that all my students have had that education from me, that I've challenged them over their educational process to demonstrate that they understand what they're doing. That it's not just the answer that is given, it is what it means. What problem did you solve? Have you included the essence? Have you excluded what is not necessary at this point in time? And not thrown everything into the bin and crank the handle and come out at the other end with very elegant things without really being responsible for understanding what it is and what it means and in which direction to move. And that is a point that both in my teaching in classes and with my graduate students has been probably one of the hallmarks of the way in which I try to educate people.
Uri, I'd like to thank you very much. It's been a pleasure. I appreciate your willingness to spend some time talking.
Thank you, Walter.